Hi there, my name is Amra and welcome to the showcase video for my final year project. The problem with strategy games is that, well, they're complex. To understand why, we're gonna need to understand what the branching factor of a game is. Let's take a game of chess as an example. The situation you see on this board of chess, let's call a game state. In order to move from one game state to another, we perform actions. Now, this information we can represent as a tree diagram, where a node represents a game state and an action is represented by a line. Thus, you get from game state to game state by performing actions. Therefore, the branching factor is the number of children at any given node, and therefore you could also calculate the average by averaging this out of all the nodes that you have. For chess, the average branching factor is 10 to the 123, although compared to other games, this number is fairly small. Other strategy games have much larger branching factors, and therefore this is a field of really interesting research on how can we create an AI agent that could cope with these large branching factors and play well. Therefore, we're introduced to the core of this project, a game called Tribes. The average branching factor of this game is 10 to the 1500, far larger than the average branching factor for chess. This game is a re-implementation of the Battle of Polytopia, which in turn is a version of Civilization, just simpler. This is where my project comes in. The aim of my project is to implement two AI agents called OEP and EMCTS for this game. These agents were originally created for a game called Hero Academy. Now in that game, these agents perform really well, amazingly well. Now there are two things we should note down about Hero Academy. The first thing is that it has a smaller branching factor than Tribes. And the second thing is, in Hero Academy, you make a fixed number of moves per turn. In the original report, you made 5 moves per turn, and you have to make 5 moves that turn. However, in Tribes, you could be making 1 move, and then 5 turns later, you could be making 10. Therefore, this makes this project a little bit more complicated of implementing these agents. Now let's talk about OEP and EMCTS. Surprisingly, both of these agents are actually fairly straightforward in how they work. Both of them heavily take inspiration from Mother Nature and evolution. But first, we should probably explain what OEP and EMCTS actually mean. OEP actually stands for Online Evolutionary Planning, and EMCTS actually stands for Evolutionary Monte Carlo Tree Search. OEP actually works by creating a population of individuals. All an individual is a set of actions. You then evaluate each individual by giving them some sort of score. This is where a heuristic function comes in, and all a heuristic function does is evaluate a game state and give you some sort of number indicating how good that game state is. You then get individuals in your population to perform uniform crossover. Now this is essentially just a fancy way of saying to get them to breed. You could compare this to real life, where the actions that make up an individual is essentially their DNA, and all an individual is trying to do is pass on its DNA and hopefully make the next generation better. Also, like real life, there are mutations, so there is a chance that an individual mutates and one action is swapped out for another. Now, how EMCTS works is you start creating a tree. Now, inspired by MCTS, you have a root node, which is just a sequence of actions. Now, what EMCTS says is every iteration or every time we mutate an action which creates a new node. And using some other fancy math, we could decide what nodes to mutate, where to look, and obviously at the end of the iterations, we return the best node. Now, after many iterations and many attempts, I successfully created these agents for Tribes. The way I would test these agents is by running tournaments against other existing agents and seeing their performance. And the way I would run a tournament is just putting them on Queen Mary's cluster, because God knows my PC can't handle that. The results that you could see right now are actually fairly decent. Reason being is I did not have any time to optimize these agents, because there are a lot of parameters that you could tweak in order to increase their performance. Future work around these agents would probably include improving them by tweaking these parameters and seeing what works and what doesn't work. It should also be added that I did not have enough time to have the agents look forward and start simulating the opponent's turn just due to the complexity of that task. Thank you so much for watching. For more explanation and detail on how and what I did, you can find the rest of the information in my report.